Um, all right then. Okay. Well, hello everyone, and welcome to my talk on, well, how to crash a graphics stack pretty easily. It's actually really easy, but that's not really the point of the talk. The point of the talk today is to talk about how to do rendering at extreme render distances and ray tracing pretty much. So, uh, so what are the current problems with rendering? Well, the issue is basically we want far render distance. We want as much render distance as possible. That is why mods like distance horizons um, and far planes 2, fastcraft 2, all of these other mods exist really. So we want really far render distance pretty much. We've also got packs, which can, especially the 3D resource packs, can absolutely explode vertex count into the hundreds of thousands, if not millions. So at 32 render distance, your game will consume more than 12 gigs of VRAM. Unfortunately, these are actual things that do exist, and they are not very fun to deal with. So, what are the past solutions? We've got all the different mods that have in some way optimized the game for the game's rendering in some way or another. We've got, your standard Sodium, Canvas, Vulkan mod, Optifine, Fastcraft 2, and then the other two are Farplanes 2 and Distant Horizons, which both do rendering with LODs, which is a very critical part of the talk that will come on later. So this is what, as you can probably, this is what, Sodium looks like. I'm pretty sure most people, actually everyone at the con is using Sodiums. Sodium 0.4.10 off the top of my head. And so, yeah, it's vanilla Minecraft. Same with Optifine, Vulkan mod, Canvas, all of these other mods, they are just your stock standard mods that increase your increase your performance and optimizations. So, what does Farplanes 2 look like? This is Farplanes 2 with very short settings. So, where the LODs are very close together as a visualization so that we can clearly see. So as you can see at the start in the center, it is very high detail. And then as you get further and further, it gets to lower and lower details. That's LOD, which is level of detail. So this is Farplanes 2, which is 1.12.2 only. However, there is a new work. There is new work being done on a 1.16 version, I believe. I'm not entirely sure on the status of the Farplanes 2 mod, to be perfectly honest. However, the next main thing that I'm willing to bet a lot of people know is Distant Horizons, which is a very popular LOD mod that adds, well, level of details. This is, I believe, 512 render distance. And as you can see over here, it's LODs. So any stuff that's really far away gets put into small quads, and well, that's pretty much it. So how do we solve render distance? There are a bunch of issues with solving render distance. Firstly is CPU processing power. CPU-driven solutions are very suboptimal because they do not scale with the hardware, specifically GPU hardware. So that means that if you have like an Intel Core Duo or something running alongside an RTX 4090, as an example, you are going to be CPU bound probably because you're not exploiting your GPU to the full capabilities. The next major problem with render distance is that without LODs, it is n squared complexity, meaning that as your render distance increases, so does the amount of geometry that you need to render. And well, it doesn't do it in a very nice way to computer memory or computational resources. N squared is very bad in algorithms. You probably don't want n squared, especially if you're wanting to render, an entire Minecraft world. The existing solutions for CPU-driven, so the way that Sodium, Optifine, Vulkan, all of that works is very hard to multi-thread with the given way. With the current implementations, the only implementation that is not is Bedrock Edition that uses a multi-threaded BFS search. So that is why they can they can render at 96 render distance and be just fine. I say just fine running at 30 FPS at like potato GPU usage. So what have I done to solve this? Well, I have made a mod. I don't know how many people know this. I've made a mod called Invidium, which, is an NVIDIA only rendering mod. It does GPU driven rendering. It's got a 2-pass rendering conclusion culling pipeline, very similar to Nanite, which we will talk about in a bit. It uses mesh shaders, it is a 2-pass culling, meaning that it culls the sections, then the regions. It culls the regions, then the sections, and not yet the meshlets. So it uses something called mesh shaders, which is a semi-new feature for a lot of GPUs that is basically a compute shader attached directly to a vertex shader. And what that means is that we can start doing very silly stuff. So, this is what Invidium looks like, rendering a 14 gigabytes of terrain data using half a terabyte per second of memory bandwidth on the GPU. I do not know how much geometry that is, but half a terabyte per second of memory bandwidth. It's a lot. It renders a lot of geometry. This was running at 60 FPS, 60 to 80 FPS. I couldn't fit any more terrain in like GPU. It was memory bound. Without adding or doing better vertex compression, you are limited by the amount of memory that your GPU has to render the Minecraft world. So half a terabyte of memory bandwidth on the GPU chip itself. Per second, it's using half a terabyte of bandwidth. As I said, I haven't been able to run into a computational limit with this. It's all to reach below 60 FPS. It has always been just VRAM, always VRAM bound. However, this is not enough, not even close. So we want to solve render distance. That is having it, render far like 128 chunks is good, but it's not good enough. The aim of the talk was infinite render distance. That is not infinite. So No LODs means O n squared scaling. We need LODs. LODs have issues. You saw with the distant horizon screenshot, if you zoomed in, you could see it on the side there. If you saw, you could see individual quads. However, if we look at the NVIDIA slides, there are no LODs in NVIDIA. As you can see, each individual quad is rendered individually, meaning that there is no detail lost. Even when you zoom in to the image, it is still pixel accurate to what the actual geometry is. So yeah, we need LODs. They are a key requirement. So how do we solve this? We need subpixel LODs. Pretty much. So that is the pixel. The LODs are less than a pixel in size. Thus, you can't actually notice any difference between LODs and pure geometry. That is perfect. So this is very similar to Unreal Engine nanites. I'm not sure how many people know a rough internal working of nanites, so we'll get into that. But yeah, so subpixel LODs are very damn good and are the solution because LODs basically equal log n scaling with geometry with respect to render distance and geometry. So nanite, I am not going to explain the entire nanite pipeline. It is a very complicated beast made by a company with a lot more money than I have, unfortunately. So what nanite does is it also does a two-pass occlusion culling. So it does what's called a high Z culling, meaning that it basically takes it renders geometry that was visible from the previous frame. It generates a high Z buffer from the depth buffer, which is basically create half the image size and take the minimum depth of the 2x2 pixels that you are sampling from. That is a high Z buffer. What that does is it allows you to do basically you can sample a point on the high Z buffer and test if that point is visible, no matter the size of your AABB bounding box. So it also has sublinear scaling, or also known as subpixel scaling. What that actually means is that a subpixel is basically you can't tell the difference between if you were rendering geometry like directly, so in like 10,000 quads, or a single pixel. You wouldn't be able to tell the difference basically because, well, your monitor only has a certain amount of resolution. So it nanite also does deferred material rendering. So that means is that it doesn't have a fragment shader. It does the fragment shader in the deferred paths, meaning that the complexity of the fragment shader is only dependent on its scales with your screen size, not the amount of geometry that you are rendering, which is also really good for performance. They also surprisingly do software rasterization on any triangles that are less than 32 pixels. They just chuck it in a compute shader and call it a day, and they say it's 3 times faster than hardware rasterization, which is pretty damn impressive if you ask me. So what about my solution? We need and want subpixel LODs. That is a critical requirement. To make it look perfect to pure rendered geometry, and also because LODs means that we have logarithmic scaling, so we can get infinite render distance. So it is indistinguishable from pure geometry rendering, and it is a requirement. Why it is a requirement? Well, here we go. So to determine the point such that we can merge a block into a less than merge two blocks into less than a pixel is pretty simple. Yeah, it is a linear equation, kind of. It's kind of a linear equation. It is a linear equation up until you get f of v, which exists, yes. It is a linear equation at the very center of your screen. However, on the side of your screen, so when you're at 170 or whatever type of FOV you're using, you will notice that the pixels are more squished together on the side of your screen than are in the center. This causes some pain points because it's not a linear equation. However, what I've done is I've just assumed that it's all linear and call it a day. So to compute, so for a, as you can see, for a 70 FOV at 440p, the distance that is required for a block and a block to be less than a pixel is 54 chunks render distance, or at 4K it's 81 chunks render distance. What this also means is that at 108 chunks render distance, we can merge two blocks into a single pixel. That is very critical because that merged blocks becomes a single data point, which is an LOD. However, since it's already less than a pixel, you cannot actually distinguish it from pure rendered geometry. So what that means is that each time you go out a distance, the amount of each time that you merge two blocks, the amount of distance that you can traverse before needing to merge two more blocks doubles, which means that results in your logarithmic, your log n scaling, because it becomes 2 to the n off the top of my head, like render distance scaling with the number of distance, which is really good because that means that we can do infinite distance, render distance. So before I go on, let's talk about what some previous techniques are. So the way that previous voxelization or like voxel rendering is, we can assume that at these render distance, we can assume that Minecraft is basically a voxel game, even though up close it is not. As you can see, like especially with mods like the cleaved blocks from Yitter and other things, they are not voxels. They have angles and other shapes. However, at extreme render distances, such as 500 or whatever render distance you want, these blocks become less than a pixel, and so you cannot distinguish them between a triangle, square, circle, whatever you want. It all just becomes one. So what are the previous render techniques? The previous rendering techniques use either a VA, like a sparse voxel octree, a normal octree, a brick map, or some other dynamic acceleration or static acceleration structure. These are very good in changing scenes where geometry is changing, etc., because they can be created on the fly. There is a different technique though that is pretty common among like static scenes. I'm not entirely sure, but it's called ray marching, or using SDF, which stands for signed distance fields, ray marching. So I've got some examples of how SDF works in 2D. And so as you can see, it takes you start your ray, you sample the biggest circle available until you hit some geometry, and then you just step to that point, rinse and repeat up until you hit something that is less than some epsilon distance. You can see in both of these examples roughly how they work and how they are dynamic. This is not good enough. This is the fastest way you can render something, kind of. This is not good enough. Well, not good enough for me. So what I am doing, I created my own system called UAD, which stands for Unsigned Access Distance. It is very similar to ray marching. SDF. It's very similar to SDF. However, it is got 3 dimensions instead of just, a circle. And so what it is it's an AABB around a point. It is a lot faster to traverse through a voxel world, up to 2 to 4 times SDF ray tracing, if not more, in my experience. Implementing LODs is really trivial with it. Like, as I'll explain in a bit, it's really trivial to implement LODs because you can just halve your render distance. You can just halve your ray distance and switch to another ring. The cons of it, it's much more expensive to build than compared to a normal SDF or other solution. SDF using it like a different distance metric. It is because you are doing 3 times the amount of work. However, it definitely pays off given the amount of speed. So how is UAD implemented? So as you can see, these are some examples of some UADs. So the black square in the center is our point that we want to compute a UAD for. And then what it does expands in each axis. So this is a 2-dimensional image for demonstration purposes. It works the same in 3D, except with another axis. But it will expand in these 2 axes until it hits a blocking point. At which point, that's the size of that axis. And so it means that when you cast a ray through it, you can accelerate straight through a lot more geometry than you can if this was, you could only be bounded by a square or something. It is a lot faster than your other metrics, in my testing at least. So how do we combine this all together into an infinite ray traced acceleration engine system rendering do hickamabob? So the way that I have implemented it is with rings. Each ring contains 12 areas. Areas are 128 by 128 TLAS uints, pretty much. They are uints, and they either point to a substructure, so a BLAS or bottom level acceleration structure, or they represent a UAD acceleration point. So these areas and sections are independent with respect to the UAD, meaning so the TLAS and BLAS don't really have much of anything to do with each other than the fact that the TLAS can point to a BLAS. And BLAS is a bottom level acceleration structure, so that means it also only stores air or a block and block color. So areas can only store UAD, or pointed to a BLAS. That's each point into this. So these rings, when you're tracing, you trace from the, let's say, the blue to the orange. And then the way that so with respect to the LODs, because remember, we assumed that 64 chunks render distance is when we can halve the amount of size, basically. So we trace through our rings. Each different colored ring represents the same amount of area. So it is It is 128 by 128. But you can see in the unscaled version or the scaled version, as you go out, each ring represents more and more geometry, even though the area size is the same. So this purple and blue, for example, store the exact same amount of data. It's just that the purple is in practice 4 times the distance away compared to the blue or orange. Um, and that means that each time you double your distance, uh, you're only using half the amount of memory as you were before. Like you only add half the amount of memory as before. It is quite literally 2 to the power of n render distance with yeah, with respect to distance. So with all of my very bad speech kind of out of the way, how does this work in practice? Well, I have a very bad demo. This is extremely bad, extremely dodgy. It doesn't represent the full extent of this. But yeah, as you can see by the little title below it, this is running at 4K at 1,300 FPS, rendering 30 million blocks away. That is quite far for those who don't know. 30 million blocks is the basically the distance to the edge of the world. The Minecraft world is no, it's not a real Minecraft world, sadly. No, I didn't have time to finish this presentation as much as I wanted to. I would have loved to have a demo, but other shit has come up. But yes, so each different color that you can see in here is a different pixel, pretty much. I have actually zoomed in a lot on this image. So this image was originally meant to be taken from 0, 0. I am actually 64 chunks out. This was running at like 3,000 FPS when I was rendering it at 0, 0. It's just because I'm so close up at the moment that it's rendering a lot slower. But yes, this is very cool, and it shows the promise of this technology. Yeah, it shows that it is possible to render Minecraft at an infinite render distance on a pretty much any type of hardware. This GPU that I was using was a 3080 Ti. However, I don't think people will be running 4K 1300 FPS Minecraft. You could easily do you know, a 60 FPS 144p pretty on, I'm not entirely sure, or whatever, 144p 1440p, whatever you want to do. But yeah, it shows the possibility of this technology, and how we can use rendering to do whatever we want, pretty much. The line in the middle is actually just a wall being looked at straight on, for those who are asking. But yeah, the very center, you can't really see it, but in the very center, that is 30 million blocks out, and it is not taking that much that much storage on my GPU because of the way that the UAD system works. It's a lot more performant than I thought it would be, to be perfectly honest. So yeah, that is my solution for solving infinite render distance. Unfortunately, I don't have a full demo. I would have loved to have a full demo. But yeah, unfortunately, I didn't have time, and I got distracted on maybe another project, just a little bit. Yeah, so hardware ray tracing. It is a talk about infinite render distance and ray tracing. We can't forget about the ray tracing, but it's the spicy stuff. It's the stuff that everyone wants because it basically beats Bedrock Edition. Yeah. The only difference between Bedrock Edition and Java Edition is pretty much that they have, the funky DLSS and ray tracing stuff. So we want to do that as well. It is very hard because of because it's written in OpenGL Java Edition. Yippee! It's hard. It's not the most fun thing to do. Ray tracing still requires ON squared memory. However, it is still fundamentally ray tracing is logarithmic in scaling compared with respect to geometry. Research will need to be done on using LODs with ray tracing. I have not looked into that, to be honest. I've been more focused on laying the foundations of ray tracing in Java Edition. Oh, boop, there we go. So for those who know, these bottom two images were done last year in November. Using hardware ray tracing. So these bottom images were running very well. This was a terrible system. Terrible, terrible, terrible. It had CPU stalls, GPU stalls, memory crashes. It literally only ran on my machine. I'm pretty sure it caused other people's machines to just straight up crash. So, unfortunately, I have spent the last past few months rewriting this entire system into its own mod, which I am hoping to actually release relatively soon. Hopefully in the next month or less, which is what this top image is representing. It is representing the current night. It's on my GitHub if you want to go and see it. It does work. However, you will need to write your own ray tracing shader for it. There are not any instructions yet. In fact, the README says #does not work yet. Because, it doesn't work. However, it will enable shaders written in Iris to use hardware accelerated ray tracing. So, for example, all of the path tracing shaders that make your FPS go to absolute garbage? Well, this can run those absolute... This should, if done correctly, mean that those shaders can run at, I don't know, 60 to 120 FPS at over 32 render distance. In my testing, I'm actually not entirely sure why Bugrock or Bedrock, whatever you want to call it, only supports ray tracing up to 24 render distance, because it is the ray tracing hardware is very clearly capable of doing so much more. Last year, when I was testing the system, I was able to get I'm not really sure how much render distance, but it was insane amount of render distance using pure ray tracing at 32 samples per pixel, and it was still outperforming Bedrock Edition. It's insane what this technology has to offer, and I'm really happy I can work on it. And it is possible to add ray tracing to Minecraft, and who knows in the future. So we could potentially even add DLSS, everything and anything that we want to Minecraft in the future. Yeah, that's pretty much it. Unfortunately, I don't have much else to talk about except what's next. So what next? I would love to try and continue to develop these things. Like Invidium. So Invidium is still very early stages. It doesn't even do half of the things that it should be doing to improve performance. For example, I was doing some statistics actually earlier today on a laptop. It was only rendering 40 million quads, which is not a lot. Um, it is a lot, but it's we can do so much better with something called meshlet culling. So a meshlet is a mesh of 32 triangles, and we can use those high Z buffers that I was talking about earlier to cull them and do inline instancing on 3D resource packs. What 3D what 3D resource pack instancing, inline instancing means is that earlier I was talking about how these 3D resource packs just explode geometry. Like you can't even do 32 render distance without your VRAM and your entire other system RAM filling up. With inline instancing, you can probably do 3D resource packs up to whatever render distance you want at any resolution. So that means that what we want pretty much is nanite bit for Minecraft blocks, because I think that would just look so cool. That's my end goal, is to basically make nanite for Minecraft along with infinite render distance. I think that will be really cool. Get ray tracing all done. But what is next? Um, I want to finish up integrating Vulkan into the Iris pipeline is my goal. Adding some new stuff to the Iris pipeline is something that I really would like to do. Give shader developers access to more stuff so that they can do more cool things like they already do. I don't know if you've seen some of the shaders, but shaders like Kronos are, are more photorealistic than Blender. It is quite insane what they do. They are not real-time shaders, but they are written in fucking Minecraft with F in an Optifine format. Like, I don't think people understand how terribly designed the Optifine shader format is. But yes, what is next? Who knows? Rendering is evolving all the time, and who knows what's next? It will be really interesting to see, and I will be really happy to. I'm happy to help contribute to the next generation of rendering. Thank you very much for coming to my talk. Any questions or anything?
Yeah, I sent it in the question thing.
Okay, I'm not entirely sure how. There we go. Okay. So, well, was this all implemented in the NVIDIA pipeline or separate mod or something else? So it depends on exactly what you're talking about. The UAD acceleration structure was originally in the pipeline, yes, but as I was developing, I was like, no, I don't want to launch Minecraft every 2 seconds. And so it's currently just in like a micro application because the UAD application is just pure shaders. It is basically just a single OpenGL shader file, and that's it. The Vulkan stuff is completely separate. That code mod that is compatible with AMD and hopefully all other things that support ray tracing. But yeah, I haven't tested it on any of these systems because I only have an NVIDIA GPU. Surprise, surprise. But yes. Is there any hope for of those of us on older NVIDIA cards and AMD for to achieve these insane render distances? With NVIDIA, no. However, the UAD acceleration system is pure OpenGL 4.3 or something. It just requires SSBOs. So yes, it should work on like iGPUs and other things. Hopefully, as I said, I'm still researching and developing this technology. Um, it will require still a lot of work. However, I do hope to eventually get there, and I do believe that it is possible to do insane rendering on very sub-powered systems. Approximately how much will decrease CPU and RAM usage? Not entirely sure what you mean by this, but doing a GPU driven pipeline means that the CPU is basically free to do whatever it wants. So for example, NVIDIA can stabilize your frame times quite a bit because it doesn't have to write out a command buffer per frame for every chunk that it's rendering 3 times. It's a bit finicky and complicated, but yes, it will decrease the amount of RAM. Maybe it depends on implementation specific details that I'm not entirely sure of. Okay. Yes, it should. TM. At the moment, no. At the moment, no, because Vulkan interop is for some reason OS specific. Yippee! That means that I need to write a memory allocator implementation for Linux, pretty much. But other than that, yes, it should just work on Linux. Will this work on non-RTX cards? I'm assuming this is talking about the ray tracing. I am not sure. I'm not entirely sure exactly what it's what cards support ray tracing using the Vulkan acceleration extensions. So I'm not doing anything custom with the Vulkan ray tracing. So whatever support the driver gives you, that's what you get. I'm not going to be emulating ray tracing for the hardware accelerated ray tracing system. Yeah. How does ray tracing demos? It's a rewrite, pretty much. The old Iris ray tracing demos, which I wrote, were complete and utter garbage. Like absolute. If someone was trying to use that in production, that is a god awful idea. No, the old Iris ray tracing demos were terrible. They had CPU and GPU stalls all over the place because that was the first time I had used Vulkan. I didn't know how to do anything pretty much. And so yeah, they were absolutely terrible. It had memory leaks everywhere, would crash. So how is it different? It's faster. The new Vulkanite system has the foundation support for entities as well, which is very critical, but insanely hard to do in Java Edition due to the way that entities are done in Java Edition. If you ever wonder why your FPS goes to 0 whenever you look at like a single chest, entities are to blame. It's terrible. It's absolutely terrible. The way that entities and tile entities are rendered in Minecraft. But yes, so it's a lot better. It's a complete rewrite. It's multi-threaded. The new Vulkanite render system is all multi-threaded. Yeah. I recall you saying that one of the view distance extenders had a secondary requirement to function like an app of search. Second thing, and what does not entirely sure what you mean by this.
I was referring to NVIDIA, I think is what I was.
NVIDIA has the requirement of having a new NVIDIA GPU, so it uses something called mesh shaders, which is only in OpenGL, which is an NVIDIA OpenGL extension that requires the Turing architecture or newer, which for those in numbers is the 1600 series or newer.
So if you don't have a NVIDIA, it's a new NVIDIA. It's not gonna work as is.
Nvidium, no, that is why I called it Nvidium, because I wanted to tinker with these new technologies that I had never seen used before in any other game. So Nanite also uses the concept of meshlets. However, and they do support mesh shaders. Actually now there's an option for you to use mesh shaders. However, I'm not using them in the full way that you can yet. So I expect like I could increase performance maybe by 20 to 30% on NVIDIA, more things, if not more. I just haven't had time to tinker around with everything yet. Oh, that's a big text. Is this assuming that all blocks are voxel shapes incorrect? For example, if I had a horizontal plane of leaf block screen, yep. On a horizontal plane of diamond blocks, blue represents the leaves as fully opaque. Yes, actually, this is absolutely correct. You cannot. So one thing that I wanted to add to the presentation, but once again, no time, was how to do LODs on voxel geometry. So the current plan that I have is to take into account the transparency of the object, or the amount of area that an object covers per axis, and then make it a probability field of whether a ray passes through that block or not. And that would give the effect of being some stuff being transparent and some stuff not. And it would mean that, yes, leaves, even at extreme render distance, you might be able to see through. Same with scaffolding, actually. If you say scaffolding, I wouldn't recommend, because scaffolding has 34 quads per block, which is just an insane amount of geometry for a vanilla block. But yes, if you cover like at Y 300 or something and look down, even if you fly way up, you can still see through it. So yes, that is something that I did want to emulate. What has the 34 quads per block? No, scaffolding. It's actually insane. Yeah, no, scaffolding is very intensive. It's kind of dumb. Can you use ray tracing to figure out what's 9 plus 10? Probably. How will mod compatibilities with Vulcanite? Also, global initial. So mod compatibility should be near 100%. So at the moment, it's the same as Nvidium, where it just mixes into the sodium chunk builder and extracts the geometry from that directly. So yes, I don't see any incompatibilities directly. As for global illumination, that would be up to shaders and shader people to implement. I am not a graphics person. And ironically, I don't know how to do pretty shaders. I really struggle with making stuff look nice. I can make stuff run fast, but not look good. As for global illumination, I would like to try and provide as much support as I can for stuff, for shader packs and shader people to implement stuff like Lumen, which I think would be really cool, and or other really dumb things like DLSS 3.5 and other really weird things that no one ever thought would be possible in Minecraft. Can you explain the rainbow image at 30 minutes? So this one? This rainbow image, I'm assuming, or do you mean the other rainbow image on the last slide? So this one, each single different color, I know it's terrible because this is also a JPEG image. So it looks like absolute garbage. Each different color that you can see represents an individual block. So you can't actually see, but around here, if you zoom in really close onto yes, there are 3 vertical walls of blocks. If you zoom in really close over here, you can actually see where the merge point is because I am zoomed in on the image. Like I walked closer to it. So normally you wouldn't be able to see it. It just looks like a bunch of noise because everything is meant to be subpixel. So it looks absolutely terrible in person, but it's doing everything correctly, which was the test of everything. In order of comparisons, how much faster is the actual extreme distance renderer system from vanilla or beetroot edition? So I'm assuming this is talking about the difference between NVIDIA and vanilla. Is that correct? So the difference between NVIDIA is that it is all GPU driven. To render a world, no matter what size. So let's say, I actually, yeah, I'm running NVIDIA in this pack. However, there are known issues with newer drivers that cause it to break when you enter the cyberpunk area. Anyway, yeah, I can render. So in the world where, hang on, let me see. Is it going to load? There we go. So, in this world, this is rendering I'm not even sure. This was rendering like 12 gigabytes of terrain geometry per second, per frame or something. It was dumb. It was only around 50 OpenGL render calls. It was like not so it was all GPU driven, meaning that the amount of render calls is the same no matter how much you're rendering, which is not true for any other mod really. Yeah. So GPU driven like rendering means that you make the GPU do all of its own work. It generates its own work pretty much. So no matter how much you are rendering, it is all the same amount of draw calls. For the ray tracing, what GPU did you test on and what would you expect the lower end ray tracing GPUs? I do not know. I have a 3080 Ti and a 3070 Ti laptop. That is all my testing equipment I have. I haven't even tested it on the 3070 Ti laptop. Well, I have, but like it runs fine. I don't have any low-end GPUs to test with, sadly. As cool as that would be, I don't have money really to get a spare GPU to test performance with. As much as I would actually like to, but I can't. As much as I would like to try and test and optimize for these lower end GPUs, the best I can do is just open MSI Afterburner and do 20% power. Okay, serious question this time. How well is this expected to work for different versions? Forge, I don't care about because I use Vulcanite. I'm assuming this is talking about Vulcanite. The Vulcanite is use it with sodium and iris specifically as hard requirements. If a mod such as rubidium and oculus, or I think it's oculus, I'm not really sure, wants to do it, I'm sure they like it's just 3 mixins. The amount of mixins that Vulcanite has is around 5 or 6. It's like potato amount of mixins. You can probably port it to like rubidium and stuff in all of 10 minutes to 30, 10 to 30 minutes. But that is not something I support because I am only supporting iris and sodium directly. Same with Nvidium, actually. Someone posted a patch for an older Nvidium version to work with rubidium, and it was like a 3 kilobyte patch. Would this thing work on a Raspberry Pi 4? Probably. I'm not sure exactly on what specs the Raspberry Pi 4 has in terms of OpenGL support. However, you could probably, if you want to do software rendering, you sure as hell could. But yes, if the CPU / iGPU of the Raspberry Pi 4 supports it, then you could probably use it. Yes. Will AMD ray tracing, or whatever exactly AMD calls it, be compatible with Minecraft with the rendering once that mod comes? AMD ray tracing is the same on. So the way that ray tracing works is it's done via Vulkan extensions. That the Vulkan extensions being that define how ray tracing works, pretty much. As long as your GPU supports these extensions, it will hopefully, assuming there are no driver bugs, which is absolutely a lie, it will work, ideally. So yes, it should just work, especially the newer Vulkanite version compared to the old Iris ray tracing demo. Yeah, it should just work, TM. It looks like that is all of the questions. Does anyone have any other comments, questions, suggestions, anything else they would like to ask? I am happy to answer anything, but yeah, thank you very much for everyone for coming. I hope you enjoyed my talk. Perfect. Thank you.